Hello trigonometry students, my name is Jamie Amy and this video starts our discussion on chapter 3, which is in radian, measure, and the unit circle. The common unit for measuring angles other than degrees is radians. A measure of an angle in radians is the length of the arc intercepted by the angle. If no unit of angle measure is specified, then the angle is understood to be measured in radians. So if you're given a question and you see theta and it doesn't say if theta is in degrees or radians, we assume it's in radians. If you see theta equals, let's say for example, 30, that's a pretty tempting one to think that that's in degrees, but if there's no degree symbol, it's in radians. Let me show you the contrary. If you see theta equals 30 degrees, then our question, we're working with degrees. Okay, if not, we're working with radians. How many radians does it take to go halfway around the circle? So use the figure. If this is 1 radian, how many of those would it take to go halfway around the circle? Pause the video and try that now. Welcome back. If you said approximately 3, nice work. Let's have a second one, maybe to right here, a third one. You might have thought the third one would reach all the way around. It's close, but it's actually 1 radian, 2 radians, this third radian, and then a little bit more. It's actually approximately 0.14 more. So you may have seen this value representing our answer, 3 plus a little bit more, or we use the symbol pi for that. And it's approximate with 3.14. All right, pause the video and try the second question. Welcome back. If you came up with 2 pi or 6.28 or 6 plus about a fourth more, then you got it right. Nice job. So if it takes 3.14 to go around this direction, we can visually, we can show that again. Another 1, 2, 3, and here's our remaining 0.14 approximately. So that would get us to, let's count up, 4, 5, 6 full radians, and then we've got this approximate 0.14, 2 of those. So the answer is, once again, 6 plus about a fourth more, or 2 pi. Okay, I found a video that has a lot of graphics behind it, and I want us to watch it together as a class now. It's going to explain what I just explained here, but instead of them writing on it, they've put some nice graphics to it. So if you did not pick up on the concept we were discussing here, we've got another chance with the video.
In the previous video, we looked at how angles are measured using degrees. This angle would measure around 30 degrees. A right angle would measure 90 degrees, a straight line 180 degrees, and one complete rotation 360 degrees. Do you know why 360 degrees? It's somewhat arbitrary and had something to do with the base 60 number system. Do we have some other way in which we can measure angles such that it makes a little more sense? Yes, that brings us to the concept of radians, and trust me, not many people understand what radians mean. Most people know how to convert from degrees to radians and vice versa, but it ends there. To understand what radians mean, let's draw a circle. Let point O be its center and length R be its radius. Now let me take this length R and place it here at this point. Now all I do is push it onto the circumference of the circle. The length of this red part is still R, it has just become curved, and that's all. The curved length R starts from here and ends here. Now, from the center of the circle, we draw another radius that joins the other end point of the red curve. This length will also be R as it's the radius. Let's analyze the figure. We have an arc of length equal to the radius of the circle and 2 radii joining the center and the endpoints of that arc. Remember, the length of the arc is equal to the radius of the circle. This angle formed here is 1 radian. That's the concept of radians. Actually, there's radius everywhere around this angle. R, R, and R, And that's probably why they call it radians. According to various scientists and mathematicians, this is a more logical way to measure angles. It's because we are measuring the angle in relation to the radius of the circle. But how are radians related to degrees? What would this angle be equal to in degrees? If you understood the concept of radians well, then understanding the conversion between degrees and radians would be a walk in the park. What is the circumference of a circle? It's 2 pi r, where r is the radius of the circle. We are talking about the circumference, which is the entire boundary of the circle. Now listen to the next question well. How many such arcs would you need to cover the entire boundary of the circle? Let me repeat the question. How many such arcs of length r would you need to cover the circumference of the circle? The length of the arc is r, and the circumference is 2 pi r. Yes, 2 pi r. It means we would need 2 pi such arcs to cover the circumference. 2 pi arcs? What does that mean? As pi is approximately 3.14, we would need 6.28 arcs to cover the circumference. How would it look? This is 1 arc, 2, 3, 4, 5, 6, and a little part left for 0.28 arc, or 28% of an arc. So we need 2 pi arcs to cover the entire circumference. And what does each arc correspond to at the center? We have seen that 1 arc corresponds to 1 radian at the center. It implies that to complete 1 full rotation, we would need 2 pi radians. And it tells us something more too. If we rotate 1 arm completely, then 2 pi radians will be covered at the center. But wait, hold on. We also know that 1 full rotation equals 360 degrees. Yes, 1 full rotation equals 360 degrees. As both equal 1 full rotation, these two will be equal. 2 pi radians will equal 360 degrees. That's the relation between degrees and radians. This is what we have been working towards in this video. If we understand this, we can easily derive the rest. This is 1 full rotation. Then how many radians will 180 degrees be equal to? If we divide this equation by 2, we get pi radians equal to 180 degrees. And 180 degrees is half circle or a straight line. And what about a right angle? If we divide this equation by 2, we get pi over 2 radians equal to 90 degrees. So a right angle is equivalent to pi by 2 radians. These three relations are most important when it comes to conversion between degrees and radians. And we don't really need to remember all three. Knowing just one is enough, and we can derive the rest. And now we come to the last and the most important point of this video. What does 1 radian equal to in degrees? If we divide the first equation by 2 pi, we get 1 radian as 360 over 2 pi degrees. Substituting the value of pi as 3.14, we get the approximate value of 1 radian as 57.2958 degrees. That's the degree measure of 1 radian. If we have an angle like this, which measures 1 radian, it will equal 57.2958 degrees.
And that was that pi mini radians is equivalent to 180 degrees. Since these are equal, we can use them to convert from degrees to radians should we need to, by making one the numerator and one of them the denominator. For example here, pi radians over 180 degrees. Since those are equivalent, the value of this ratio is 1. You can take the reciprocal here, so 180 degrees over pi mini radians, and again, you'll get 1. So either of these can be useful if you're starting in radians and need to convert to degrees, and the other one is useful if you're starting in degrees and need to convert to radians. And I'll show you how to choose which one now. Okay, the example asks us to convert between degrees and radians. So the first question here, it is 45 and the unit is right there, it's degrees. So we're going to figure out how many radians that is using one of these conversion formulas. Okay, we want to choose the one in green right here, pi radians over 180 degrees, so that our units cancel in such a way that we strategically end up with radians. So hopefully you can see here that the 45 degrees, it's currently a numerator if you write it over 1 for visual. That's going to cancel out with, and you need your other degree symbol or units of degrees to be a denominator so that that will cancel out there. And then our remaining units is radians. So now we just need to do 45 times it by pi, divide it by 180, and we'll get our value of pi over 4, and we have the correct or requested units, which is radians. All right, pause this video and try part B. Welcome back. Let's see how you did. If you multiplied that by pi radians over 180 degrees, your setup is right. Nice work. And if you reduce that to negative 3 pi over 2 radians, you got it right. All right, let's work through part C together. We have negative 5 pi over 6. There's no degree symbol, but the word radians is there. So we're in radians, and the directions for this example, if you recall, are converting between. So we are currently in radians. We need to get this in degrees. Okay, so we need to pick either this first one or this second one. Well, we're currently in radians. Our goal is to end up in degrees. So strategically, we want to pick the one in purple here. For the same reason as last time, we need our current degrees, radians, we need that to go away. So since it's in the numerator, we need the corresponding or matching unit to be in the denominator so that they'll cancel. And the unit that remains will be degrees, which is what was requested of us. So we've handled the we've handled the units by multiplying the current by this conversion here from the purple. And now we just need to do the negative 5 pi times 180 degrees divided by 6 pi. You'll see that the pi's cancel, and we end up with negative 150, and we are in degrees. Okay, I want you to try part D, but before you do, I need to ask you a question. What units is part D currently in? If you said radians, you got it right. It doesn't specify what unit it is, so we have an agreement that it is radians. Okay, so take this 4.25 radians and convert it to degrees, please. Welcome back. Let's see how you did. If you multiplied that one by 180 degrees over pi radians, your setup is right. Nice strategy there. And if you got 243.5 degrees, then you did that one right as well. Nice job. Let's see what's next. Looking at an application of radian measure. The arc length, lowercase s, is given by the product of the radian and the measure of the angle in radians. So this formula, S for arc length, is equivalent to R times theta. Notice here that it says it must be in radians. Find an arc length, so lowercase s, using S equals R times theta. A circle has a radius of 18.20 centimeters. Find the length of the arc intercepted by the central angle with a measure 3 pi over 8 radians. Okay, so we're in radians, so that's pretty good. We just get to go straight to our formula. We're going to plug this in right here for the lowercase r. We're going to plug this in for our theta. That will leave us with just one unknown, just the lowercase s, and we'll solve for it. So here we can see that figure. We have a circle. Its radius is 18.20 centimeters, and its central angle theta is 3 pi over 8 radians. All right, so we're going to find the arc length S. That would be if you're, let's say you're standing right here and you're walking, or whatever mode of transportation, and you end up there. What's the distance you traveled? What's the arc length? All All right, we're going to use the formula S equals R theta, because that arc length, if you think about it, it's got to be dependent on, well, how big's the circle that you're traveling around, and then at what angle measure is going to determine where you stop. Okay, so we're going to plug R in, that's 18.20 centimeters, and theta in, that's 3 pi over 8 radians. It looks like this. We see the centimeters for the 18.2. We don't see the radians, the word radians for 3 pi over 8, but we know that's okay. And we're going to simplify that. And it turns out that that arc, starting here, walking to here, is approximately 21.44 centimeters. So thinking at that critically, the radius of the circle from here to here, 18.2 centimeters. This right here, a little bit longer, so 18, 19, 20, 21, about 3.24 centimeters longer if you walk this versus if you walk this right here. In this example, we're asked to find the length using S equals R theta. Okay, we have a picture here and a description. A rope is being wound around a drum with radius 0.8725 feet. Okay, so we have a drum here. Radius it's less than a foot. It's 0.8725. How much rope will be wound around the drum if the drum is rotated 39.72 degrees? So let's look at the figure again. Here's the rope. So the question is, how much of this rope? Well, this rope is taking on the shape of the arc as the drum rotates. So we want to try to interpret that or translate that question into how much rope is being wound around into one of these variables. How much rope is being wound around the drum would translate into lowercase s. That's what they're asking us to find right here. So we need R because it's dependent on the size of the circle or drum. We got it. We're going to plug that in. And we need theta. And we've got 39.72 degrees. Problem. We're in degrees. We're going to need to switch that to radians before we can apply this formula. All right, let's do that. The length of the rope wound around the drum is the arc length. So we're going to use S equals R theta. This is just what we were talking about, but here it is written up nicely with the angle converted to radians. Okay, so we're going to plug in our R, 0.8725. We're going to plug in our theta, 39.72, but we're going to multiply that by pi over 180 degrees. You can do this separately if you want to. If you want to do this first, converting the 39.72 degrees into radians, you can do that first if you want, and then come back to the formula, or you can do your conversion right here in the formula. Okay, either way, we cancel. These degrees are going to cancel. This right here was given to us in feet. We don't need to write radians because it's understood. And so when we simplify that, it's approximately 0.7649 feet. So let's take a look at that here. The amount of rope wound around the drum is closer to half a foot. It's approximately 0.6049 feet. So thinking about this, if theta increased, so if we rotated the drum more, the arc length would also increase. If the radius of the drum, if we used a larger drum and we rotated it 39.72 degrees, the arc length would increase as well. So arc length, lowercase s, is dependent on the radius of the circle and theta in radians. This example is about finding an angle measure this time using S equals R theta. Two gears are adjusted so that the smaller gear drives the larger one. If the smaller gear rotates through an angle of 225 degrees, how many degrees will the larger gear rotate? Okay, this one, we want to stay nice and organized with our work, our thought process here. So I have it divided into two parts. First, we're going to figure out S, R, and theta for the small gear. Separate from that, we're going to figure out S, R, and theta for the large gear, so we don't get our variables and constants mixed up. Okay, so let's start with the work for the smaller gear. We have our formula in its general form, S equals R theta. We're going to plug in what we know, which is theta. However, our theta needs to be in radians, so we take the given 225 degrees and convert that to radians. The other thing that we know is R, which is 2.5 centimeters. This is all for the smaller gear, okay? So we plug in our 2.5 centimeters and our 5 pi over 4 radians, and we calculate, and it turns out that the arc length, 12.5 pi over 4 centimeters. It says that two gears are adjusted so that the smaller gear drives the larger one. If the smaller gear rotates through an angle of 225 degrees, so let me just give you a visual. If that were the initial side right there, and then we rotated 225 degrees, that's bigger than 180, so maybe about here. This would be 225 degrees or 5 pi over 4 radians. Then we just figured out that the arc length is 12.5 pi over 4 centimeters. Well, if these gears are rotating and they're in contact with each other that entire time, then every point on the smaller gear would match up to the same amount of points on the larger gear. What I'm getting at here is that let's pretend this is the initial side of the larger gear. Not quite sure where it stops, but I do know that the arc length is going to be the same as it is for the smaller one. So maybe to write about maybe this length right here and this length or distance, if you want to think about it. Maybe those are the same, approximately. What I'm getting at is the arc length, or lowercase s, for the small gear is the same as it is for both gears, the large gear and the small gear. So here that is written up for you. The arc length s will be the same for both gears. Okay, so let's use our formula, S equals R theta. We're working with the large gear now and plug in what we know. We know that S is 12.5 pi over 4, and we know that R is 4.8 centimeters. We don't know theta. We leave it, it's unknown, and that's okay. We're going to use our algebra skills now to isolate theta. To isolate theta, we would need to get rid of this multiplied by 4.8. We do that by dividing both sides of the equal sign by 4.8. Now it looks like this. Theta equals 12.5 pi over 4 times 4.8. If we do those calculations there, we have approximately 2.045, and that is our angle. So our units are radians. And that answers our question that the larger gear rotates through an angle of 117 degrees. So it went a little past this approximate 90, maybe to right about here would be the terminal side for 117 degrees or 2.045 radians. And this arc length would be the same, 12.5 pi over 4 centimeters, as it is for the smaller gear. The area of a sector of a circle is the portion of the interior of a circle intercepted by its central angle. You can think of it as a piece of pie. You can see here, almost looks like a triangle, but it's not. It has this one curved side like a piece of pie. The shaded region is a sector of the circle. The area, capital A, of the sector of a circle of radius r and central angle theta is given by the following formula. Capital A equals 1/2 of the radius squared times theta, and for this formula we also need theta to be in radians. Let's try one. Finding the area of a sector-shaped field. A center pivot irrigation system provides water to a sector-shaped field with the measures shown in the figure. Find the area of the field, round to the nearest square meter. Okay, so if our field were a rectangle, we'd use base times height. If our field were a square, we'd do side squared. If our field was a triangle, we would use 1/2 base times height. But the shape of our field is a sector. So we're going to use the area equals 1/2 r squared theta. Looks like theta is given to us in degrees, so we need to switch that to radians. Let's do that conversion here. 15 degrees multiplied by pi over 180 is pi over 12 radians. So this is pi over 12 radians right here. So when we plug in our variables r and theta, we've got the 221 meters, and we've got pi over r for theta. Now we simplify this here, and we're talking area, so our units are going to be square meters. All right, I'd like you to pause this video and do homework questions from chapter 3, numbers 1 through 16. Thank you for being here. My name is Jamie Amy, and I will see you next time.